Welcome back, everyone. This is Dr. Coil. Today, we're going to wrap up Faraday's Law and talk a little bit about some of the applications of it. Now, remember, Faraday's Law talks about induced EMFs or induced voltages from magnetic flux that changes in time. So the right-hand side of Faraday's Law is the cause, and the left-hand side describes the effect. So we talk about the rate of change of magnetic flux inducing a voltage that is described by the value on the left-hand side. Now, there are three ways that we've talked about having the flux changing in time. First, there's the possibility that the magnetic field is actually changing in time. So the magnetic field changing in time actually leads to what we talked about as a curly electric field or a non-conservative electric field, the E vector that shows up on the left-hand side of Faraday's law. We could also have the second way, flux changing in time by changing or moving the area with respect to the magnetic field. And third, talking about changing the orientation of the magnetic field with respect to the area, whether we're changing the vector direction for the magnetic field or the vector direction of the area that defines the flux changing in time. Both the second and third way do not create a curly electric field as in state one, but rather induces a voltage or the EMF that comes from the result of the vector cross product between the velocity vector and the magnetic field that shows up on the left-hand side of Faraday's law. Okay. Now, there's also one other very important aspect that shows up on the right-hand side of Faraday's law, and that has to do with the negative sign. And the negative sign is so important that there is a name for it. It's known as Lenz's law. And basically, what it describes is that the induced phenomenon, whatever results, either we're talking about the induced voltage or prior to that, the induced magnetic phenomenon, whatever gets induced will actually oppose the change in the system that caused it. Okay? Now, what is another application of Faraday's law? And that is where it leads us to talk about transformers. And of course, I'm not talking about this type of transformers, but rather the everyday practical applications that leads to electrical use in our everyday lives. And the transformers that I'm actually talking about is simply a device for taking current in one circuit and causing or moving, in a sense, it to another circuit, possibly transforming the voltage in the process, thus the name transformer. So here you see a picture of two separate coils, coil one on top and coil two on the bottom. And through the center of these two coils, we have placed basically an iron bar to more or less confine the magnetic phenomenon that goes from one coil to the second coil in the same fashion. So in this particular example, we have the same areas as defined by the coil one and coil two. If we run a current in coil one, it could induce a current in coil two by creating a magnetic field in coil one that flows through the metallic bar through then the center of coil two. Now, if the flux through coil two changes in time, we get an induced voltage or an induced current, depending on how we want to calculate it. So here is an example of the calculation. Same exact picture, same exact scenario as before. And as we can see, we know because of the bar that we have placed through coil one and through coil two, that the magnetic field that gets generated in coil one is the same magnitude as the magnetic field that actually goes through coil two. So I've denoted that as B1 equal to B2. And given that the areas of the coils in this example are exactly the same, then the magnetic field through coil 1 going through the areas of coil 1, we're going to call flux 1, that must then equal to the flux through the secondary coil, because the magnetic field strengths and the areas in this example are identical. Now, if flux changes in time through coil 1, then similarly it will change through coil 2. So the rate at which flux 1 changes is exactly the same as that through coil 2. So the flux 1 dt is equal to the flux 2 dt. And of course, we've shown that we can actually talk about the induced voltage in relation to the change in magnetic flux. So the voltage in 1, subscript 1, is equal to N1, that's the number of turns in coil 1, times the rate of change of magnetic flux through coil 1. And similarly, we can write exactly the same expression for coil 2 with the subscripts 2. Now notice, since we actually have the rate of change of magnetic flux through 1 is equal to the rate of change of magnetic flux through 2, I can simply relate the expression for voltage 2 with what I've actually denoted above with the voltages. So here we have voltage 2 is equal to the number of turns of coil 2 times the rate of change of magnetic flux through coil 1, which is the voltage through coil 1 divided by the number of turns in coil 1. Therefore, I simply have voltage in coil 2 as a ratio of the number of turns between the two coils times the voltage in coil 1. And you can basically make voltages go up or down in coil 2 based on the ratios of the two different coils. And that's more or less how a transformer works. We could step up the voltage or step down the voltage. Now, this is one configuration of a transformer. So here's a clicker question. If I hook up a 9-volt battery to a 200-turn input coil, that would be coil 1 of a transformer, that then has a 400-turn output coil, or coil 2, what is the output voltage in coil 2? Now go ahead and think about it. Pause the video for now and go to the Long Kappa topic 3G lecture folder and open the induced voltage clicker item and answer the question. Welcome back. I hope you noticed that the expression from the previous slide has to do with a rate of change. Think about whether anything is changing in time for this situation. Now, let's go ahead and do a calculation example, something known as the Tesla coil. Now consider the following circuit. So we now have a slightly different looking configuration of the two coils. There's the coil 1, which is in red in your picture, and there are less number of turns in coil 1. And through the center of coil 1, we are going to place coil 2, which is many more turns. And coil 1 here in the picture is connected to an alternating current voltage source, and then there is a gap, is denoted by the two lines coming out of coil 2. They're basically metallic conductors that are separated by a distance. Yeah. So let's look at how we would analyze the following circuit, and exactly how much induced voltage that we can get out of coil 2 given a particular input voltage that is an alternating current signal into coil 1. First, we recognize that for coil 1, or here solenoid 1, the voltage that we're talking about is simply the voltage of the alternating current input. That is going to allow us to relate to the time-changing flux, the rate at which the magnetic flux is changing in time in coil 1. Here I have total, which is basically the number of turns of coil 1 times the rate of change of magnetic flux through one turn of coil 1. So now I can actually rearrange the previous expression by basically defining that the rate of change of magnetic flux in one turn of coil 1 is equal to the input voltage V sub AC divided by the number of turns in coil 1. So the flux in one turn of coil 1 is equal to the ratio of the area A1 over A2, that is the cross-sectional area as defined by each coil, 1 and 2, times one single turn of magnetic flux through coil 2. So if I actually relate that to the rate of change, it's exactly the same ratio, as you can see there. We know that the rate of change of magnetic flux in one turn of coil 1 is equal to the input voltage VAC over number of turns in coil 1. So I'm just simply replacing the left-hand side of the previous expression with what we know numerically, and set that equal to A1 over A2 times the rate of change of magnetic flux through one single turn of coil 2. So now we can actually rearrange that expression so that we actually know what the rate of change of magnetic flux in one turn of coil 2 actually is. And of course, the total amount of magnetic flux in coil 2 is simply the number of turns in coil 2, that will be N2, times the rest of the expression that we have just derived. So the net voltage, total voltage, that comes out of coil 2 is the number of turns in coil 2 times the expression above, which results in this. So the voltage that actually gets induced in coil 2 is simply related to the input voltage, VAC, multiplied to the relative ratios of the areas and the number of turns. And if we were to put some numbers to this expression, let's say coil 1 has 10 turns and coil 2 has 10,000 turns, and that the input voltage is about 15,000 volts. The areas A2 versus A1 could be designed to have a fraction of about an eighth or a quarter or whatever you desire. Remember, this is actually a schematic setup or an example, but if you were to build this, you can actually decide exactly what the area of coil 1 and the area of coil 2 happens to be. But if you do a rough estimate in terms of the quick calculations, N2 over N1 is a factor of 1,000. And if A2 over A1 is, say, a factor of an eighth or something like that, multiply that by the input voltage of 15,000 volts, I think you can see that the voltage induced in coil 2 is somewhere in the millions of volts. Okay, so the bottom line is this: you can actually step up voltages with a simple setup of two separate coils, not physically connected to each other, but coaxial as in this picture, and you can create voltages in the millions of volts. And if you reverse the order, you can take millions of volts and drop it down over multiple steps of the same exact setup to actually have voltages that are more or less at 120 volts, or the ones that are actually in your typical home wall outlet. Now, this is actually part of the power transmission in terms of our everyday lives and electricity usage and so on, going up and down in voltage. However, some other folks have actually created something fairly useful. Remember, the input voltage signal is an alternating current, so it oscillates at a particular frequency, which means the output voltage, the induced voltage out of coil 2, is also going to be oscillating at a given frequency. And when people figure this out, they've actually created something fairly interesting. Well, I hope you enjoyed a little snippet of that, but if you like to see more, plenty of other people have created videos such as this on YouTube. You can go ahead and search for singing Tesla coils, and you'd be surprised at how many different types of music people have actually done this with. Okay, we're going to move on to a slightly different topic now, and I'm going to stop this video for now. And you can go ahead and click on the next video that has to do with inductance. See you in a bit.